Thank you very much. Let me take a second to thank the organizers for giving me a chance to talk and also for organizing this wonderful conference. I'm a PhD student at Columbia University, and I will talk about some joint and ongoing work with my advisor, Daniel Lacker. Let's see if I can figure this out. OK. So we study making laws of equation, a making laws of equation of this type, where you have the dynamics of xt are given by a drift, v, that depends on the law of the solution process, and then some additive Brownian motion. So models of this type arise in many applications, in physics, in finance, and in machine learning. And often, it's of interest to perform a numerical implementation of these models. So this is a bit tricky, essentially because we don't know the drift. Somehow the drift, knowing the drift requires knowing the law of the solution, but that's what we're trying to learn in the first place. And the way this is usually attacked is with a particle method, where we take a system of n particles, y1, y2, up to yn. And then we run this as d here at the bottom, where we replace the law of the solution process by the empirical measure of the particle system. So the idea here is that if the number of particles n is large, then the particles will be approximately independent, and each particle will behave approximately like the making laws of left. So this phenomenon is called the propagation of chaos. And what we want to do is to quantify exactly this propagation of chaos. So there are many ways to do so. We choose to measure it in relative entropy, where the relative entropy between alpha and beta is the usual integral of the log density ratio. Now, we fix the number of particles to be n. And then we take pi k to be the law of the first k particles out of n. So the state of the art is that if v is nice, in a way that I will elaborate on in a second, then the relative entropy between the law of these first k particles compared to k independent copies of the limit should be of order k over n, with constants that depend on time and a bunch of other stuff. So this was proven years ago, I think in the 80s. At least in dimension 1. But there has been some recent work by Dan that pushed this envelope a little bit. And in particular, Dan proved that if V has this pairwise interaction structure, essentially V is linear in the measure argument, then you can go beyond this k over n, and you can actually get the considerably faster rate of k squared over n squared. So now, this pairwise structure is quite rich, and it covers many, many applications of interest, especially in physics. But in some models, especially the ones in my title, so mean-field langevin dynamics and mean-field games, you naturally see non-pairwise interactions. So our question was, can you take a more general V that is allowed to be potentially very nonlinear and still get this sharp rate of k squared over n squared? The answer will be yes, but of course, there's a price to be paid. So this is our first theorem. We need to assume that V has 6 bounded derivatives in the space and measure arguments, and the starting condition is sub-Gaussian. And then we get that we maintain the sharp rate of propagation of chaos of k squared over n squared. So here, by derivative with respect to a measure, I mean Wasserstein derivatives. Those are the ones that we look at. I want to sort of comment on this requirement a little bit. The boundedness requirement is not super sharp. We need the first derivative to be bounded, and higher order terms are fine. But of course, 6 derivatives is a lot. Now, to some extent, so we don't think this is. The domain of V, we take the whole space. In principle, the subsets should be fine, but then you have to be careful with how you define the SD, right? In principle, the SD can go outside. Thank you. So why is this not unreasonable? On one hand, this is satisfied in many applications, or we check that it is satisfied in many applications. But on the other hand, this is sort of unavoidable because we're dealing with a very general function of the empirical measure. And somehow you take a function of the empirical measure, and this is known to converge quite slowly to a function of the real measure in I dimension. And here we're really working with d-dimensional particles, right? This rate is dimension free. And so in some sense, some smoothness is required. And sort of as a baseline, this sort of state-of-the-art suboptimal result of k over n for general V already requires 3 derivatives. So another way to put this is if you give us 3 more, we can go considerably faster. Okay. So I mean, you can essentially take some function f from Rd to Rd to R d, and then take, I don't know, f of f, big F of p and x, which is just this function of the mean of p x and x, right? So you take f to have 6 bounded derivatives, and then it fits into, yeah, so big F would be v. Yeah, exactly. Sorry, to stick to the notation. And for instance, in the pairwise interaction, f needs to be identity. So it's quite a bit more flexible. Yes.
Yeah, I guess we're just like excited about this.
I am not sure. I would have to think about it. Yeah, probably, but yeah, exactly. So the thing is, modification in Wasserstein space is a bit tricky, but you can do something. Okay. All right. So I have 2 main applications: mean field games and Wasserstein gradient flows. I will focus on Wasserstein gradient flows, and then at the end I'll speak briefly about mean field games. So often in applications, people want to solve mean field optimization problems, which are optimization problems over the space of probability measures of some function f, which has this composite form. So f is given by some psi, which is has to be quite general, but is usually smooth, and then a differential entropy component that sort of makes the problem a bit more convex and a bit nicer. So of course, this is an abstract setup, but you can put a lot of sort of statistical problems in this under this description. So equilibria computation in continuous games, empirical Bayes, people have done neural networks, and so on and forth. So motivated by these applications, there's this nice paper by Hu, Ren, Shishka, and Spruch in 2021, where they study the so-called mean field langevin dynamics, which is an SD, where the gradient is taken to be minus, the drift is taken to be minus the Wasserstein gradient of the potential psi. So the reason why this process is interesting is if you look at the law of the solution process, then this law is a Wasserstein gradient flow in the sense of Ambrosio-Gigli-Savare of the functional f. And under reasonable assumptions, this law will converge to a minimizer of f. So this provides sort of a very flexible tool to attack these problems. Just implement this SD, do a particle method, and then hopefully, if the function is nice, you're done. So this immediately motivates sort of an interest in a particle method. And this is our second result. The point of this process is that we care about the long time behavior. So what we prove is that under some convexity assumptions on psi, in particular strong convexity along Wasserstein geodesics, provided that the convexity parameter is big enough, then we get a uniform in time propagation of chaos result, meaning that we can take a supremum over all positive times, and our estimate stays the same. All right. So I have less than 1 minute to talk about mean field games, so I will go super fast. The punchline that I want to give is that you can use our methods also to study mean field games and mean field control problems. So often people care about these n-player differential games where each player controls an SD and plays against the opponents. And then in these games, you can characterize Nash equilibria by a particle system of NSDs that interact with each other. And people also care about the large n limits of these games, so mean field games with the population of players is plus infinity. And even here, you can characterize sort of the mean field equilibrium, the solution of the game, by an SD. In this large population limit, the SD will be of Makin-Vlasov type. And the quick punchline is that you can use our methods to also get this sharp propagation of chaos in terms of the optimal trajectories in Nash equilibria versus mean field games. We still get the k² over n² rate, which cannot be improved. We have to go sort of to a slightly weaker W2 distance, but the punchline is very similar. Thank you very much. Thank you for listening.